Good morning, everyone. Welcome to our NMIS Insights online webinar called Cracking the Code, Python for Data Analytics. I'll just now pass you over to Sam Hume, who will shortly start the presentation. Thanks for joining us today.
Thank you kindly, Deborah, and good morning, ladies and gentlemen. The National Manufacturing Institute for Scotland welcomes you to this morning's NMIS Insights online webinar entitled Cracking the Code, Python for Data Analytics. The speakers this morning, we have Dr. Andrew Hamilton, Mr. John Riley, and Mr. Paul McHard, all members of the NMIS Digital Manufacturing team. And before we begin, ladies and gentlemen, a few housekeeping rules to run through. This webinar is being recorded and will be made available on our YouTube channel. Your microphones and webcams will be turned off during this session to avoid background noise. You can type your questions throughout the session via the chat tool, and we encourage you to do so. Time will be allocated at the end for speakers to answer your questions. Use the hashtag NMIS Insights for any questions on Twitter at NMIS_group. Please take time to complete our survey that will be sent after the webinar. What is the National Manufacturing Institute Scotland? The National Manufacturing Institute Scotland is a group of industry-led manufacturing, research and development facilities where research, industry and the public sector work together to transform skills, productivity and innovation to attract investment and make Scotland a global leader in advanced manufacturing. NMIS will increase productivity by reducing barriers to innovation, will stimulate investment and increase manufacturing competitiveness, will catalyze job creation and strengthen supply chain links, will inspire and attract talent and equip current and future workforces with the skills they need and businesses need, work with manufacturing businesses of all sizes in multiple sectors, providing benefits across the whole of Scotland. To that end, we are very much part of a One Scotland team. NMIS is operated by the University of Strathclyde and is supported by the Scottish Government, by Scottish Enterprise, by Highlands and Islands Enterprise, by the High Value Manufacturing Catapult, by Skills Development Scotland, by Renfrewshire Council, and by the Scottish Funding Council. And in this infographic here, we have described the NMIS Group, which is a combination of core NMIS capability, specialist technology centres, and an active network of partners in the manufacturing community. In the yellow, I'll draw your attention to our specialist centres, which are open now. The specialist technology centres, the Advanced Forming Research Centre and the Lightweight Manufacturing Centre, as you will, I'm sure you're well aware, are very well established. In development, we have our temporary workshop space and our outreach via NMIS networks. And in the pistachio and teal, we have the core elements that will open in 2022, the Digital Factory, Collaboration Hub, and the Manufacturing Skills Academy. We are not waiting for the Manufacturing Skills Academy, Digital Factory, and Collaboration Hub to physically open. Work has already begun, and we're open for business. The Manufacturing Skills Academy already has continual professional development courses in place, and work is already being done for the Digital Factory by the AFRC's digital team. So in summary, the new NMIS building has been approved, will open in 2022, work has begun, and NMIS is open for business and here to support you. Thank you. And without further ado, it gives me great pleasure to introduce our first speaker this morning, Mr. Paul McHard.
Thanks, Sam. So thanks everyone for joining us. Today's session, if any of you joined us for our first Python-based webinar back in, I believe it was the beginning of May, we presented a lot of information about why Python is a valuable asset to learn how to use it and why it can be a powerful tool superseding Excel moving forward for business. today's session is kind of following on from that very much so, but it's going to be a technical demonstration running through the entire workflow of creating a machine learning model. We're going to load in some initial raw data from a manufacturing source, and then we're going to go through the stages of preparing that data, analyzing it in a valuable way, and then using it as the input for a support vector machine, which is a form of machine learning algorithm. I'm going to use that to show the value that this has to you as a business. So what we're using for this presentation is the presentation mode of a Jupyter notebook, but just a note on using Jupyter notebooks for development tasks. They are incredibly useful tools when you're in the initial stages of working on a Python-based project. They kind of present similar to a kind of a Google Doc sort of format. Your code is live and interactive, so when you've programmed in a function, you want to test if it works, you can just run it there and then in a small code block, and that will instantly give you the results of whether or not that code has worked and what the results of your code are. So it's really useful for the kind of initial stages, and it's very easy to collaborate with others on, as we will show you throughout. So I'm going to pass on to John, who's going to give you the first few stages of this workflow.
Thanks, Paul. Yeah, so before we take a deeper dive looking into our machine learning and the data analysis, I'm just going to speak to you about the libraries and we're going to use in Python, and also how we're going to set up our data. So the first library that we're going to be using is NumPy, and as it says there, it's for mathematics, but it's for complicated mathematics, so it's like saying of matrices, so the multiplication, addition, so things which computers are really good at, and they can do it quickly. Next, we'll be using pandas. Again, pandas is for accessing our data set, and it's also for organizing it. Matplotlib will be used for the visualization of the data and creating graphs, just so we can understand more what's happening in the data sets, because as humans, we see patterns in graphs more than we do in a big list of numbers. And then finally, we will be importing the SciPy library, and today this is for scientific functions, and today we'll be using it for the linear algebra. Just to bring a wee note at the bottom, we're using the from-to import syntax here for our SciPy methods here. So this just allows us, when we're calling the find peaks method, all we need to do is type out find peaks, and this just saves us a little bit of time if we're not having to type out the entire thing each time we want to use it. Now I'll speak more about the machine learning tools that we're going to use in this session, and we are going to use today is the Scikitlearn for our machine learning functions and for the classification. Scikitlearn also has linear and logistic regression functions, which are also used commonly within machine learning. There are other alternatives for machine learning like PyTorch, TensorFlow, and FastAI. But today we will just be using Scikitlearn. I'm just going to go over a couple of definitions of machine learning methods. So there's regression. What is regression? It's a statistical method for analysing the relationship between independent variables. But today we'll be focusing on classifications, and in the context of machine learning, classification is the task of an algorithm labeling data as being in one of n categories based on its learned behaviour. And there, just in the wee box below, you see how we're importing it into Python. Now we're importing or ingesting our data set, and as you can see here, we're using pandas for our ingestion. We're using the read CSV method, and we've got our CSV file here, which is called session-data.csv. We're also passing a final parameter in here for one of the columns, which is t, and it's called parse dates, and this is allowing pandas to understand that our column t is a time series data, and this will allow us to use that in the machine learning methods you'll see later on. And as you see, pandas has printed out this lovely data set in table format. We've got all the column headings and all the data there. Just on this side, why are we using Scikitlearn? The graph below here was a questionnaire taken on the website Kaggle, which is for machine learning and data sets. And the question they asked them was, what machine learning framework have they used in the past 5 years. As you see at the top here with 66%, Scikit-Learn was one of the most popular machine learning frameworks that was used. So why is Scikit-Learn so popular? It's accessible for beginners, it's well documented and well maintained within the community. It's also lightweight, and you can develop simpler data analysis tasks more rapidly than the other frameworks. So again, at this early stage of doing some data analysis, Scikit-Learn is the framework that is suited best for testing these hypotheses out. So now I'll pass you over to Paul again. Thanks very much.
Thanks, John. So as much as it's nice to look at your data in a table format like Pandas can give you, it's also when you're trying to work with it and you're trying to see what value your data is going to be able to provide you, it can be nice to visualize that in a richer way. And Matplotlib gives us a lot of functions to do that. There are alternatives, which we'll talk about at a later stage, for visualizing data and for plotting graphs. But for now, we're going to be using Matplotlib because it's a very easily accessible and very kind of lightweight library for this. And I know it's going to look like a lot of code as we go through it, but for the most part, all it is just commands for applying formatting and the appearance of the graph. Much like if you were making a graph in Excel, it'd be much like the sort of things that you'd do in drop-down menus and stuff like that. So it's all very accessible information. So first, we're going through setting some parameters. We're just instantiating that it's date formatted data because we're working with time series data. And then these are a couple of formatting parameters that we're going to be using later. They're not particularly important. And then lastly, we want to be looking at this particular half-hour window from our data. That's what we want to visualize. So putting this into a graph, this is the code for the graph. As I said, it looks like a lot, but really it's not. We're just plotting our graph, setting up our labels, and setting a couple of parameters for how we want the graph to look. So if you're doing this in your own implementation, this is the sort of things that as you go through it, it's just line by line will become a lot simpler than it looks right now. And what that gives us when we plot it is something like this. So this is our first look at our data. This is the equivalent of just taking this table that we had before, and this is just firing it into a graph. So it couldn't be simpler. And what we're looking at here is, for context, the data that we're going to be using as we go through this is pulled from an accelerometer sensor, which is monitoring a manufacturing process and operation. And the reason we wanted to look at this half-hour window is because we're seeing in this first 15 minutes a really nice periodic signal. You've got these nice peaks with very low noise in between them, and nice and regular periodic peaks. And then in the second half, we're seeing it change to a different state where it's much more disrupted and there's much higher noise as we go along it. So that's what we're going to ultimately be trying to detect using a machine learning model later on, is the difference between this state and this state, and can our system differentiate that. So I'm going to pass you over to Andy now, who's going to talk us through how we go about actually doing that and how we'll go about programming that.
Thanks so much, Paul. Before we begin discussing feature extraction, I just want to raise one more point about why we're using a Jupyter notebook as well. The Jupyter framework allows you to separate out between a client, as user clients and server architecture. So the Jupyter notebook backend can be running on a server in a remote location, for example, on the AFRC on our high performance computing cluster, then we can connect via a web browser to it. I think for the purposes of today, Paul was running, it's actually locally on his machine, but it does give the opportunity to be able to offload a lot of heavy lifting, which is to remote high performance computing nodes, which is becoming more and more valuable when most of us are starting to work at home as well. So it's quite a flexible environment to use, especially in this climate that we're in. So what I'd like to talk about is feature extraction. So as Paul demonstrated before, in our data set, we have two areas, two different states that we know from labeled data from the manufacturing process. We know when that process is considered in good condition and when that process is considered in poor condition. And we're wanting to distinguish between the two. Now, if we try to analyze that data set by itself, there's a few methods to do that, and we could actually analyze this without generating any features whatsoever. So we could use neural networks and other approaches that would be able to generate its own features as part of its process as well. We could also use feature extraction techniques such as principal component analysis. So when we talk about feature extraction, generally speaking, we're talking about dimensionality reduction. So trying to take complex signals and combine characteristics of them into lower dimension features that can then be used to base that the machine learning algorithm can use to base its decisions on. But in terms of explainability, it's quite often a good approach to do this filtering manually and go through this yourself. This means that if you're trying to embed this process as part of a manufacturing process, you quite often have to explain this to an operator as well. So you have to make sure that this is explainable and understandable and fits within the sort of existing decision-making process that will be used by human operators. So the approach we're going to take is showing how you can go through feature extraction. So just another quick point is that whilst conducting feature extraction, a danger is to bias the data, because humans will naturally want to pick up patterns and see patterns where they might not necessarily be there. So one approach to this, when you're wanting to do manual feature extraction, is to have as many people as possible within the operational limitations of your project to visualize data and also feed this back to domain experts, in this case, the manufacturing operators themselves. So let's first of all look at the first feature we're extracting, which we're terming the baseline signal energy. So in the previous graph that Paul was illustrating, the first 50 minutes was characterized by low noise in between peaks, and fairly periodic peaks as well, where the second half is had high variance and peaks with variable frequency of occurrence. If we go back to the other slide, Paul, that's great. So one of the first areas to use is to apply a rolling filter, and I'll use a window size of 1.5 seconds, and it's going to look at the variance across that window. The reason we've chosen this is that we're trying to reduce the variability of the already low noise within the first 50 minutes compared to the second 50 minute and a half. We've chosen the 1.5 window is because that's approximately the width of the peaks themselves during the first 50 minutes. So we're trying to preserve those at the start initially as well, and see if we can really push down the noise within the first 50 minutes, whilst not affecting too much the characteristics of the second 15 minutes. So what we see in the graph below is we've managed to do that. So you can see the signal to noise ratio in the first half is better. So the peaks themselves are more distinct compared to the noise in between the signal. Whereas the second one is still maintaining that characteristic of being highly variable with lots of peaks occurring at random frequencies. However, we really want to understand the underlying energy between the two and move away from looking at the peaks themselves. So if we move into the next slide, please, Paul. So for this, we're going to apply an 8-second window. And in this case, we're wanting now to dampen the peaks themselves, and again, further reduce the noise of the energy between the peaks in the first 50 minutes, whilst maintaining the characteristics of the second 50 minutes window. So what we can see is we might really do that. So what we can see is if you ignore the peaks here, there'd be almost no energy in the signal in the first 50 minutes. Whereas the second 15 minutes would still have some energy in that underlying signal strength. So in this case, if we move on to the sort of final filter, we can here we're using the rolling median window, because that will be able to allow us to remove the peaks, which will normally form a small portion of a given distribution of the 40-second window that we've chosen here. Whereas if we apply it to the second half, it is still maintaining a lot of those peaks and the underlying signal energy. Now, just to be clear that these windows that we chose were not selected initially and worked immediately. This is an iterative process that we had to work to understand what happens. So again, automatic methods can help this, but we're trying to understand it ourselves and be able to rate that back to features that we believe are in the signal itself. Again, this is time to explainable machine learning as well. So we now have what we think is one feature. So this is the baseline signal energy. So what we'd like to do is maybe select a second feature. We could base a machine learning model on just one feature and use a decision boundary that will separate out between a given threshold. But ideally, what we'd like to do is have as many features as possible that have as low correlation to each other as possible. So when one feature changes, the other one does not change in the same direction. So wanting to make sure that we have two features that can help to separate out instances of the data set we're dealing with and really help us to create that linear decision boundary at a later stage. So as Paul mentioned, the other characteristic of this data set is the periodicity of the peaks themselves in the first 15 minutes and second 15 minutes. This whole data set is actually 7.5 days long. So we're just zooming in on a representative part, but it's a very useful part, as Paul said, because it's quite a distinction between the two areas that we're wanting to identify. So if we wanted to identify the peaks here, we probably want to have some sort of peak detection algorithm. So if we move on to the next slide, please, Paul. So when we're assessing peaks, we're looking for peak prominence from the underlying signal. And in this case, we're having to set a threshold. The thresholds are generally, you want to try to avoid using thresholds as much as possible because you're setting a hard value in which saying this is one part, this is the data I'm looking at, and this is not the data I'm wanting to look at. That's inherently biased by our own perceptions of what is considered to be prominent or not. So the idea is we can try to create a threshold optimization algorithm that will try to detect what is the best point where we will say this is what we consider to be a peak by given parameters. So if we move on to the next graph, please, Paul. What we've done here is we've assessed a series of prominence, peak prominence values and assessed how many peaks are actually detected. And what we've tried to look at is an elbow point in the graph. And an elbow point is normally indicative of when you're getting diminishing returns for having, by allowing more and more peaks to be considered as true peaks, we're getting diminishing returns in terms of computational complexity. And so what we evaluated is at that point there with the elbow points of 0.002, that's likely going to be give a good trade-off between detecting peaks and performance of our model itself. And so that's an important point. Is when you're trying to incorporate hard thresholds, you want as much as possible to try to make them flexible and appropriate for data set, and not just choosing an arbitrary value that you may think is correct. If we go to the next graph, please. So in this graph here, all we're trying to do now is we're trying to apply the peak filter that we're going to apply to the original data set, so we can tie this back into a visualized representation of the peaks. So obviously we've identified what we think the peaks are. We need to understand what is in context of the data set. So if we move on to the next slide. So we've superimposed the detected peaks back onto our visual data set. And as you can see, the peak detection algorithm works quite well from a visual perspective. In the first 50 minutes, we're capturing all what we would consider to be true peaks. And in the second half, we're collecting, identifying a lot more, which is what we're wanting to do. Because as you can see, the period between peaks in the first 50 minutes is approximately 45 to 60 seconds. And the second half, it's much more variable. We can see at just before the 12:30 mark, we actually have a slight error there where two peaks have been identified. And that's sometimes an issue that will just happen. And it's not always the case that you'll be able to accommodate for every single scenario. But as long as you manage to accommodate for the majority as much as possible, that's normally the best approach. If we go to the next slide, please. So now we have two putative features, which is the baseline signal energy and the inter-peak time. Now, for us to assess those properly, we need to assess them over a given window size. So say in a 5-minute window, what is the average inter-peak time and what is the average underlying signal energy? So in this case, we evaluated it across a 270-second window. Again, it's a process. But what is important here is we're now tying this back to classifications that we've taken from the manufacturing process that we know. So we know when the machine is in a good or poor state. And so then we're able to take those average block sizes and the two average features from those block sizes and say that is associated with this class or the other class. So in this case, we're looking at a binary classifier. If we go to the next graph, please. So this has plotted the average values from the exact same data set we saw before. But what we can see is in the first 15 minutes, we have a higher average inter-peak time and a lower average baseline signal energy, which is what we're expecting. When we look to the second half, that flips around and we have a lower inter-peak time and a higher baseline signal energy. And so these are the two features that we are now wanting to use to base a decision on using a machine learning model. And if you go to the next slide, please. So at this stage, it's probably good to visualize what this actually means in practice. So as I said before, we have labels to, we know what the data, the manufacturing process state is for each of these instances of these two features. So the first thing is we should probably plot those in a scatter plot to see how they look like. Next slide. So as we can see, we're plotted an x-axis into peak time and a y-axis the baseline signal energy with the log of that just to give greater separability for the purposes of visualization. As we can see by just looking at this, that it does seem that we've attained a degree of separation with one cluster around on the sort of upper left half and a less dense cluster towards the bottom of the plot. What would be maybe most useful is to look at the classes themselves superimposed on top of these plots. So in blue, this is the labels. We've labeled those periods of time for those features as either 0 or 1, representing to good or poor manufacturing process quality. So in this case, we then can see that our two features are approximately be able to separate out the data set according to our desired classification. And so the next stage we're wanting to do is create a boundary, a decision boundary in which we can base decisions on that can happen automatically. So any new instances that happen will be automatically classed as either 0 or 1, blue or red, or whatever this may apply to your given manufacturing process. It's worthwhile noting though, you can see that the accuracy is not going to be entirely 100% for this classifier, because a lot of areas that may be, so in case of some of the red dots, which are representing the poor quality data, the poor quality manufacturing process, that is, some of them are actually appearing within nearby the centroid of the good quality data. The good quality data, the features are indicating good operational state of the manufacturing process. This happens quite often when you're in binary classifiers, when you have maybe other states of the machines that are not being accounted for, or very minor transitory states that are not, you can't really classify them properly. In this case, we're just going to accept and deal with this. And so the next stage is for us to now try to create a decision boundary that will allow us to, on the whole, and within the majority of cases, make the right classify the data using these two features with the majority of the time accurately. Next slide, please, Paul. I'll now hand over to Paul now, who will be discussing the sport vector machine itself. Sorry, I wasn't too sure on that slide. So
yeah, just to piggyback on what Andy was saying just there, just an important point tying back to our use of libraries, like all the maths that has been done to aggregate the time series data for one of the earlier graphs for organizing the data and for the feature analysis, all of that has been done just by calling these functions from NumPy, SciPy, and then using as we go on using Scikitlearn. And it really is just like, it's the value of these libraries that we haven't had to explicitly program any of this. So if you're doing this in MATLAB, for example, you might have to do you might have to explicitly program a lot of these functions yourself. Whereas Python is so valuable because it's got such a large community that is actively supporting all of these libraries, and they've got a really sort of like vibrant ecosystem that goes well beyond what we're talking about here for a lot of different machine learning and artificial intelligence based approaches that really abstract a lot of the complex functionality down to just calling functions, which is just makes it really easy to rapidly deploy. As soon as you know what it is that you're trying to do, you can just soldier ahead and do it. So yeah, so what we're going to try and do is we're going to plot a linear decision boundary. I don't know if you can see my mouse moving across the screen, but we're going to try and plot a linear decision boundary right here in between the two main clusters. And again, going back to what Andy was saying about dimensional analysis and principal component analysis, you can, in your own deployment rather, you can use those tools. You can use that math to analyze your data and try and get the best sort of separation of your features and the best kind of independent variables that are going to put into your machine learning algorithm to give you the most sort of value out of your process. So going on to talk about the support vector machine is one of the simplest kind of implementations of machine learning algorithms. So that's why it's the one we're going to focus on today. It's really useful for doing these kind of classification tasks where we're trying to find a linear decision boundary. It might not necessarily be linear. We might have a data set where we've got a sort of a polynomial distribution around the data set that we want to analyze. And in other cases, that might be what you're trying to isolate, what you're trying to identify. So while ours is linear, yours might not be. And support vector machines are just as good at doing that in any case. So we're going to try to plot a linear decision boundary. And the first thing that we have to do before we can get going with our support vector machine is splitting up our data set. So as we've said, the initial graphs that we've been going through had just been using a half-hour time slice for illustrative purposes, but really we've got data that's been gathered over a whole week, over a whole full 7 days of operation. So we're split that evenly into, and when I say evenly, I mean in a balanced manner, into our training and test sets. So in the graphic below, we've got a training, validation, and test set. In a real deployment, you would probably use a validation set, which would be maybe 60, 20, 20, as a rough guess, a rough estimate rather. But a validation set only really comes into it if you're going to be iteratively testing to try and fine-tune some parameters. So if you don't, for example, necessarily know that this is going to be a linear decision boundary, you might think it might be a different kind of curve. You might have hyperparameters that you need to tune there. So you need a set of data that that you can test on. But if you just use your test data, which is supposed to be a blind test, then your model becomes biased towards it to an extent. So it's allowed to be biased towards your training data. That's what you're trying to train it on. That's what it's supposed to learn and see and adapt itself to. But your test data is supposed to be kept completely isolated for a blind evaluation at the end. When Kaggle, as John was mentioning earlier, runs competitions, they will usually provide the training and the validation set, and then they'll keep the test set private until the models are submitted for testing. So you never get to. So that's how much your model is not supposed to see the test set ever, because it cannot be biased towards it at all. So in this case, we're just going to do a split between a training test set. We don't need a validation set because it's quite a simple binary classifier. But as I was saying before, we need to have a balance between our blue group and our red group as we put them into both the training and the test set, because if we have a training set that's all blue and a test set that's all red, for example, then we're going to have a bad skew towards the balance between our true positives, true negatives, false positives, and false negatives. As with any test, as with any kind of survey that you might see, you need a balance between all of these data points as you fire into it to get the best picture of what you're actually looking like. So the code that we're going to be running for that is quite simply, we're just using NumPy and functions from Scikitlearn to split our data into these balanced arrays. And so we don't have to go through ourselves and make sure that our attributes and labels are evenly split. Our algorithms are handling that for us. And then down here, once you've got this set up, we're just splitting it 0.2 parameters, saying that we want 20% into our test data set, and then the remainder goes into our training data. So as I said, that kind of split of 70-30, 80-20 is what you'd expect to see in these kind of situations. Really, it's the sort of thing that, that as you get going with deploying these sort of models yourself, you'll know what's going to work for your data. And usually, if you've got quite a limited data set, quite a small source to draw from, then you might want to try and optimize for as much training data as possible. So you might go for an 80-20 split, you might even go as high as 90-10, for example. But those are the sort of numbers that we're looking at for this. Going forward from that, once we've got our data set up into our training and test sets, we're going to be moving on to training the model. And I'll show you the code for that in just a second. But to illustrate what we're doing as a binary classifier, and it's quite easy to see from our data, that this is what we're trying to draw a line between. But we could just as easily have a third group, or even 10, 20, 1,000 groups, that it goes far beyond what we can easily discern as a human being. And that is, when you get to this sort of really cutting edge level, that's what machine learning is so valuable for. It's drawing these lines and drawing these boundaries and classifiers beyond what human beings are capable of discerning themselves. And in a manufacturing context, this might be that while you've got one optimal state and one suboptimal state, you might instead be monitoring a process that you have maybe two optimal states or several suboptimal states that indicate different errors, for example. And this will vary based on the domain that you're working in, the data that you're working with, and the features that you have at your disposal. So going on, this is what that code looks like. So again, really all the difficult work is abstracted for us. We're just instantiating our support vector machine right here. We're saying we want a linear kernel because we want our linear decision boundary, but that could easily be a polynomial or another function that you need to plot. We're giving it our training data for our x and y so that it can learn, and this line here, this function, is abstracting a lot of complexity. So if you were to do this yourself, this would be probably hundreds of lines of code to write your own training algorithm potentially. We're then giving it our x test data, evaluating it against itself, and then the result of running all that is, so this is just for then plotting that result. The result of all that is this linear decision boundary. So we're getting a nice line separating our data out from the left and the right hand side. And this confidence score up at the top, the F1 score, is saying that it's got about an 86% confidence in its data. So our model's worked, it's run, we've got a nice line that we can look at and see in this case, yep, okay, that's a good line down the middle, separating out our blue group and our red group as much as possible. And so we're quite happy with that result. So just to conclude, before we move on to Q&A, I'm sure you'll all have lots of questions for us. Hope you do anyway. Our model has been trained on our data. It has not been explicitly programmed to draw that line. We haven't told it where we want the line to be. We've just passed it in the data and said, figure out where the line is in between all this data. And the power of this is that we can deploy this because we've used Scikitlearn and we've used a really lightweight deployment. We can deploy this on an edge device, such as the PLC that's monitoring the system and receiving the data real time from the sensor itself. We can deploy this. It can run classification on unseen data, and it can use that linear decision boundary that is drawn to say, okay, I think the machine's in an optimal state. I think the machine's in a suboptimal state. And really, this is the power of machine learning. So I hope this has been illustrative as to why machine learning is such a useful tool as part of a data analysis toolkit, and that's really the way that you need to see machine learning. It's not a mystified kind of massive, impenetrable piece of technology. It's a very accessible tool that you can use in a manufacturing process to kind of push forward with your digital transformation as part of your journey towards deploying an industrial Internet of Things, which is the way that the industry is going, and data analysis and all of these tools that we're discussing today underpins all of that. So I hope this has been useful. We'll now pass back to presentation for Q&A if anyone has any questions for us.
And thank you very much, Paul, John and Andy, for that clear, illuminating, informative, and we hope inspirational introduction to to coding there. We have received a few questions, it will be no surprise to you, throughout there. So perhaps if I could begin, and a few of these are more comments really. So we received a comment from Ewan, who works for a company called Filament, is a startup based in Scotland, who and they are developing a web-based alternative to Jupyter with real-time collaboration, sharing and publishing features. So perhaps they can connect with us after this, or with yourselves. Also, Ian Gibson from Seed introduced himself, and also David Ferguson, a KTP associate from the EEE department here at the University of Strathclyde, working with a company, and forgive me if I'm mispronouncing this incorrectly, David, but Turner Elseni, which is a machine learning wind turbine conditioning focused organization. There was a question from David here, which was, can you share the code which you've introduced today? Will that be available to share with participants?
I think it should be, because I think the dataset is actually hosted in Pure, which is Strathclyde's open source data repository. I'll double check that, David, but just now I don't see why not. And we can maybe create an open GitHub repo where that can be pulled from. It's part of our NMIS institution's closed GitHub repo, which we obviously can't give public access to, but I'm sure we can, at the same we can look at making it a public one, so you can just clone it from there and run it yourself and take the data set from Pure.
And thank you, David. Also, if I might ask you please to direct your inquiry to the NMIS Inquiries email address, and we'll be able to take it up with you directly. Further, we received another question from Robert Devaney. Will the Jupyter Notebook be available to view?
Same question.
Sorry,
yeah,
forgive me.
I can appreciate that it is a lot of code for us to show all in one go, and we've really just kind of skipped over the code blocks as we've gone through them to illustrate what they're doing, more than actually getting into the nitty-gritty of what each line by line, and we don't have the time in an hour to go through that. So yeah, to echo what Andy said, we can't see why not.
Thank you. And further, I suppose that those questions reflect to me. Perhaps I could ask you to comment on what support is available from NMIS in respect of establishing projects, conducting R&D activities, and perhaps receiving questions from SMEs, business, the research community, and industry in general.
We're more than happy to field any questions, so please feel free to get in touch. We're happy to discuss if it's an SME or business requirements for creating this data-driven decisions for given processes within your environment as well. Other research groups who are more than happy to work together on collaborative projects together as well. So yeah, don't hold back and reach out to us, and we're more than happy to answer your questions.
Thank you very much, Andy. Another question received. Why are you using Matplotlib for visualization and not another library like Seaborn?
Mainly because we're used to using Matplotlib. It's a lot of people. So just if the members of the audience don't know the difference, so Matplotlib is quite one of the more mature and older visualization libraries for Python. It's really, really great. I really like using it. Seaborn's got a lot of great built-in ones, so the formatting's not for you. It's got some built-in analysis as well for creating things like confidence limits, error bars, and whatnot as well. So it's a great toolkit as well. So you could use that as well, and you might be able to get some graphs, some nice-looking graphs with less code. But Matplotlib's that's the default I tend to go with. I think I'm probably the same for Paul and John.
Yeah, likewise, very much so.
Yeah.
Thank you very much.
Seaborn's your thing, you can very much use that instead.
Thank you. And another question then: why would one use TensorFlow or PyTorch instead of Scikitlearn for machine learning?
Well, they've all got different focusing. There's a lot of the approaches within you can find across these various libraries. A lot of time TensorFlow is used when you want to leverage GPUs, because it has a lot of great libraries to convert your ML approaches into data blocks which can be processed and understood by GPUs. Because a tensor is essentially it's a 3D vector. I think maybe that's butchering the definition of tensor, but but the GPUs are quite often process information in a very general way in 3D matrices. That's what they were for. So general purpose GPUs will generally want to have data formatted in that way. So Tensorflow would be quite useful for that. In this case, because the complexity of the model is quite low, it's a linear decision boundary, it was not necessary to use those. But if you have higher complexity, if you're wanting to use SVMs for higher complexity data and create dozens of 3D planes or non-linear boundaries using quadratics or sigmoid functions as well, you may want to consider using as well. And yeah, so it just depends on what you're wanting to use and what libraries. So it's always Scikitlearn as a good one to go start with, because Paul mentioned it's one of the best supported, one of the best documented. I think it's got the largest active community supporting it as well, and the open source community. But others are great too for the application as well. So it's just depending on what you need. So normally, I'd suggest you wanting to say what one is applicable for your data, look on Stack Exchange, Stack Overflow. Look out for what other people use for their projects as well. And if they suggest using certain libraries, it's probably a good idea to code in them. The Scikit-learn, if you just wanted to get up and running with trying out some machine learning approaches, I'd say it's a best bet to start out with.
Thank you.
I think TensorFlow as well, if you're dealing with, going off to the GPU acceleration, if you're dealing with convolutional neural networks or any kind of deep learning of any form, then TensorFlow's got some great libraries for that sort of thing. But again, that's going down the same route of GPU acceleration and kind of more complex models. But if you are interested in deep learning and convolutional neural networks, then TensorFlow is going to be a lot better for that.
Thank you very much. And similarly, another question from Robert Devaney. Which data formats are best for this process?
Well, it's quite flexible, because I think in our first webinar, that was one thing we talked about Python, was how flexible it is in terms of the data sets you can use. In this example, we're loading from a .csv file, which is a fairly common standard, mainly because you can use it with Excel as well. But you can be passing this data in from JSON, XML, HTML, maybe other proprietary formats, and Python allows you to create your own parsers. So you have some fairly bespoke data format that you may have to use a proprietary tool for. It may be possible to replicate that same process in Python as part of it. So yeah, that can be a difficulty to start, is getting the data to format that's useful. In this case, we're looking at time series data, so pandas is quite a good way to use it, because it's essentially sort of a mini Excel table within your Jupyter Notebook with the headings, very quick filtering methods, very quick ways to remove certain columns and generate new columns based on numeric functions of the original data as well. I'd say it's there's not any one best format. I'd say CSV is probably the most common in terms of time series data I've come across, but a lot of data sets that are getting pulled from APIs directly from the machine layer quite often will be on JSON or XML, but there's formatters for that. There's parsing tools for that as well, I believe, within pandas. And if not, there's a JSON library and an XML library as well.
Any format you can think of, pandas pretty much has it sitting there, and as you say, you can create your own. But yeah, the only thing I'd say is that the best data format is as much data as you can get. That's the key thing for machine learning. It's more getting the data, as much data as you can. What format it's in doesn't matter too much. It's actually getting useful data is key.
To quote you from our first webinar, John, pandas can do it.
yeah, exactly. Pandas can do most things.
There we are, and thank you very much. So, Robert, I hope that answers your question. Forgive me for having almost certainly mispronounced your surname there. A final question then that's been received is, in respect of NMIS testbeds, we've recently introduced the resume testbed. I was wondering, we've received a question, does machine learning play any role in the systems architecture design?
It's one of the main it's one of the core functionalities we're wanting of it. So with the resume testbed, we're developing the infrastructure for the hardware infrastructure for a digital factory. But the hardware infrastructure is only part of the value of it. It's the software services that sit on top of that, and we're wanting to create a framework we're developing a framework that will enable machine learning models to be developed in a centralized high-performance computing cluster. And then ideally, we can push some of those out to edge devices. As part of this project, myself, Paul, John, other members of the digital team are working on this, the various aspects of it. And the idea is we want to make it as flexible as possible. So if you were wanting low latency, you might want to have your machine learning or statistical model, doesn't necessarily need machine learning, pushed quite close to the edge. So the inferences based on that can be made quite rapidly. In some cases, the complexity of the data analysis that you're doing will be too much to use the resources of, say, industrial controller. So you might need to pull that back to the more centralized container orchestration platform that we're developing as well, and anything in between as well. So it would depend on the type of data, but yeah, the model development, deployment, and improvement over time is a key feature that we work on this. And we're working with industrial partners and members of EMMAS on this to make sure that this is oriented toward the manufacturing sector.
Yeah, I think as well, as I noted in my sort of closing point, these kind of data analysis tools very much underpin kind of the sort of industry 4.0 IoT ideas, and Resume as a testbed couldn't be more aligned to those same ideas. You know, it's very much what we're trying to push for with the digital factory and with Resume as a testbed. So yeah, data analytics can be a big part of Resume, as Andy detailed.
Thank you very much. Well, I suppose that will end the Q&A portion of the webinar and succinctly bring us to an end. So all that it remains is for me to thank the speakers, Andrew, Paul and John. Thank you very much indeed. To thank the marketing team for their hosting and their organization, seamless as ever. Thank you very much. And finally, ladies and gentlemen, to yourselves for your attendance and continued participation. We welcome your inquiries and your participation. So we look forward to hearing from you and seeing you at the next ENMIS Insights webinar. Thank you very much.
Thanks, Sam. Yes, and just to reiterate, thanks very much for joining us today. And thanks to our presenters, Paul, Andrew, John, and yourself, Sam. Shortly after this webinar ends, we will send out a survey. We would appreciate it if you could take a few moments to complete this for us. Your feedback helps us shape future events that we're organising. And if you're interested, our next ENMIS Insights webinar is taking place on Wednesday, the 21st of October. It's Meta Skills Future Proofing the Workforce with presenters from the ENMIS Manufacturing Skills Academy and Skills Development Scotland. You can find details of this and register on our website at enmis.scot. I'm just going to bring this webinar to a close now. Thanks once again for joining us.
Thank you.
Thanks.
Thank you.
Thank you.